Hi everyone, this is Miss Leia and in this video, we're going to talk about image formation in mirrors. Specifically, we're going to talk about the law of reflection and how it applies to image formation in mirrors. So I'd like to start by showing you a simple demonstration that I did at home, and it's composed of just very simple materials we readily have at home. So first one is a plain mirror, a laser pointer, and then a body spray to simulate mist. You may also use water instead of the actual body spray. Now, because this is a very simple experiment with no appreciable hazard, you may actually try this at home. So what I basically did is there's this mirror, and then I projected the laser light onto the mirror, and then I sprayed the mist on this particular region for the light rays to be visible. So it's gonna look something like this. That's when I was spraying the mist or the body spray. Okay, so this is a screenshot of how it looked like. Okay, so I'd like to emphasize a couple of points here, and I'd also like to introduce a few terms. So the laser was here, and then the light that strikes the surface of the mirror is what we call as the incident ray or incident light, while the light that bounces off the surface of the mirror, that's called the reflected ray. Okay, now there are two key concepts here. The first one is light travels in the path of least time. In short, it takes the shortcut, the shortest route. So if this is the laser pointer, it will take a straight line path until it hits a barrier, which is a mirror. Okay, you call it the Fermat's principle. So the consequence of the Fermat's principle is that light travels in a straight line path for it to take the least time. Second thing, light rays can bounce off a surface, especially if it's a reflective surface. So you can see here that it bounces off, and that's what we call as a reflected ray. And this phenomenon is called reflection. Now, it's not just mirrors that are capable of manifesting the phenomenon called reflection. It can be some other things like a metallic mug, water, for example, even eyeglasses, right? So those are some of the examples. Okay. Now, light rays don't just bounce off at random directions or random angles. We have what we call as the law of reflection. To elaborate that, if this is a surface, for example, let's say it's a mirror or any other surface, flat surface that can reflect something, that line, which is perpendicular to the surface of the reflective object, is called the normal line. And then the incident ray, the one that strikes the surface, the angle it makes with the normal line is the angle of incidence or theta sub I. And then the reflected ray, the angle it makes with the normal line is called the angle of reflection or theta sub R. And what the law of reflection says is that when reflection happens, the angle of incidence is always equal to the angle of reflection. Of course, I did not discover that myself. It's been known to ancient Greeks since a long time ago. And of course, it has some practical applications. Just to discuss one quick application of the law of reflection, one example would be the periscope, which is an optical instrument. It looks like this. This is actually a diagram. So there's a hole there on the upper portion of a tube-like structure, and then another hole in the lower part. And then there's a mirror right there at a 45-degree angle, and then another mirror on this particular part. Suppose there is a tree here. Of course, it's an illuminated object, meaning to say it's visible to us because it can reflect the light rays that are hitting it, coming from the sun, for example, or whatever light source. So when there is a light ray that strikes, for example, the surface of the upper mirror of a periscope through the opening, it will bounce off, right? In accordance with the law of reflection, that the angle of incidence is equal to the angle of reflection. Now, this mirror is oriented so that the light ray will bounce and go downward towards the lower mirror. And then this mirror is again oriented at a 45-degree angle so that the light ray will be reflected horizontally towards the eye or eyes of the observer. And that is what makes the observer see something like this tree, for example, even if it is at a higher position than where the observer is. So A specific context where it is used is for submarines, right? Because even if submarines are actually immersed in the water, through periscopes, they get to see what's happening above the surface. So that's really important for them. Now, at this point, I'd like to further elaborate the concept of image formation, especially with the help of what we call as ray diagrams in optics. But this time, we're going to feature Pochi the cat. He's a stray cat, and we feed him every day. He also stays at home every day, and he's really cute and kind of chubby. Okay, so what exactly is a ray diagram? There you have the definition. You can read it for yourself. But what I'd like to do is I'd like to discuss it in the context of image formation for you to understand further what ray diagrams are. Now, suppose this is a plane mirror or a flat mirror in side view. Whenever we draw a mirror like that in optics, by convention, the left side is the reflective side of the mirror. So that's where we look at, that's where we can see a reflection, etc. And then this is the back side. Now suppose that Pochi is there, standing in front of the mirror, looking at his reflection. How will the image actually look like? I mean, how will his reflection look like? Of course, it's gonna look like a cat. It's gonna look like Pochi as he is, right? It's not gonna look like an elephant or a dog. But what I mean is that when I say how will the image look like, what I mean is what will be the orientation? Is it gonna be upright? Is it gonna be inverted? Is it gonna be a virtual or a real image? So for us to know that, this is what we're gonna do first. Okay, first thing we have to recognize the fact that Pochi is an illuminated object, and he reflects light rays in different directions. Those light rays are coming from the light source in this room, right? So we can think of an incident light ray coming from a specific point in Pochi's body. Example, the tip of Pochi's ear, right? So we can imagine that there's an incident light reflected off Pochi's ear, and I'd like to consider the one that strikes the mirror because we want to know how his reflection will look like. So that's one incident light hitting the mirror. Of course, it will bounce off, right? Because mirror is a reflective object. So in accordance with the law of reflection, it will bounce off and it will look like that. Okay, now, it's not sufficient to have this single light ray from this point for us to know how the image will be or where will it be. So what we need to do next is we will project a second incident light from that same point in Pochi's ear. So from that exact same point, okay, another incident light, but this time I'm making it hit another spot in the mirror. And of course, in accordance with the law of reflection, it will bounce off towards a certain direction. Now here's the thing. Where exactly will this particular point in Pochi's body appear? Or where will the image be formed? It's very simple. Those reflected light rays which came from that particular point, all we need to do is to find their intersection. Meaning to say, we're going to extend these reflected rays, and whatever is the intersection, that will be the location of this tip of Pochi's ear. So we're going to extend the reflected rays, and we have two reflected rays, right? I told you to have two. Okay, so there. If we extend them, they're not gonna meet given their orientation. So we're gonna extend them backwards. It's that simple. Okay. If you extend those reflected rays backwards, they will meet, right? Okay. Now, the intersection of those two light rays will be the location of this point in Pochi's body. So it's gonna be this. So this is how his image will look like. Okay. Now, Miss Leo, why did you use two incident rays? Will one incident ray suffice? Okay. The answer is that if you only have a single light ray, you're not gonna have an amplified or a brighter image in a practical perspective. So meaning to say, in a practical sense, in reality, what you need are intersecting reflected rays because that will what give you an amplified or an intensified or a brighter image. Okay. What else? Miss Leia, why did you assume that, given that this is the tip, obviously, as justified by the ray diagram, how did you know that the rest should follow like that? That this is the eyes, this is where the forelimb is, etc. So we can further justify that by showing you another ray diagram, but this time we're gonna trace the location of the forelimb of Pochi. So we're gonna, same step as before, we're gonna project an incident light from the forelimb of Pochi. Before it was the tip of the ear, but this time we're gonna trace the tip of his forelimb. So that's the incident light, of course, is gonna be reflected. But once again, you need at least two sets of light ray for you to have a bright image. So we're gonna have another incident light ray hitting another point in the surface of the mirror, and it will bounce off. And once again, same thing, you have to extend the reflected rays, not the incident rays. You're gonna extend the reflected rays, and whatever is their intersection will tell you the position of this particular point in Pochi's body. But again, if you extend them forward, they're not gonna meet, right? So what you're gonna do is you will extend those reflected rays backward so that they will meet or intersect at a common point. And that intersection will be the equivalent of Pochi's forelimb, specifically this point. So it will look something like this. Now you might say, Miss Leia, how come there's an image generated? And there are actually no light rays intersecting at that point. Those are just extensions of the reflected rays, but there are really no light rays. So how come there's an image formed? I mean, if I stood behind Pochi, I would actually see that same image as well. But how does that happen? The thing is this image is what we call a virtual image in physics, meaning to say, it's only a projection in our mind. It does not really exist, meaning to say, there are no light rays hitting this particular part in the mirror at all. Because those dashed lines, those are just projections. They are not light rays. Look, those light rays actually bounce off, right? They did not make it past the surface of the mirror. So when I say that those are just projections, what I mean is this: our brain has actually adapted to interpreting that light rays travel in a straight line path. Once again, our brain has been sort of wired or programmed to think or assume that light rays always follow a straight line path. Therefore, if you stood behind Pochi, for example, here, you would still see the same image, right, that Pochi sees. It's because those reflected light rays, when they hit your eyes, what your brain will tell you is that those light rays came from a straight line path. They followed a straight line path. So, meaning to say, your brain will tell you that those reflected light rays came backward like this. What your brain will tell you is that they came all the way from behind the mirror. And that's how the virtual image gets generated. So once again, your brain has been sort of, our brain rather, has been sort of programmed or wired to think as if light always follows a straight line path. So it will assume that those light rays came from that point. So it will also tell you, oh, the image of Poch is there behind the mirror. And yes, when you look at your own image as well, it's like there's a world, there's a physical space behind the mirror when in fact, it's a concrete wall, right? So yeah, but the brain tells you something else that's actually not quite real. So it's a virtual image. Those are just extensions of the diverging rays. They're not generated by actual light rays, and it's not something you can cast or project on a screen because there are no light rays there. This image is only in the mind, okay? So the opposite of virtual image is real image, and we're gonna talk more about that in another video. So at this point, I'd like to clarify how come for us to identify Pochi's image in the mirror, how come we only focus on these 2 points, the tip of his ear and then this lowest portion, which is his forelimb? Why did we only care about the lowest and topmost portion of his body? And then from there, we assume that the rest will follow as they are. So it's pretty simple. Suppose there is a broom, for example. If it's inside a cubicle, let's say something like that, or a cabinet or something, if this is visible to me, that on the top I see the handle and then the fibers are there at the bottom, even if I don't see the stuff in the middle, I can deduce that the broom itself is oriented upright like this. The fibers are resting on the floor. And the other way around is true. If I see that the broom looks like this, even if the middle part is hidden, if I see that the fibers are on top and the tip of the handle is at the bottom, I can deduce from there that the broom is standing in an inverted position. So it stands on the tip of its handle, right? So I don't need to see the one in the middle. If I know the opposite ends, the topmost and the lowest portion, I can deduce what's going on in the middle, right? Knowing that this is how the broom look like, or knowing that this is how Pochi looks like. So that's it. So in this case, we only trace the topmost portion of Pochi's body, the tip of the ear, and then this one, right? You could have done it with the other forelimb instead, the lowest portions, right? And once we figured out that this is the position of the topmost portion of his body, and this is the position of the image of the lowest portion of his body, then we can deduce that this is how the entire image should look like. That's it. I hope that that has been clear to you. At this point, I'd like you to try answering this concept check items in your mind, like a virtual image, just in your mind. Okay? Maybe you may write it on a piece of paper. So for you to have enough thinking time, I'd like you to pause the video at this point. So go pause the video and answer the questions. Okay, at this point, I'd like to reveal the answers to the questions. There you go. I hope that you got everything right. For this video, that's all. Have a great day.